In this web talk, I show how to use Mplus to investigate a common occurrence in latent class analysis, where direct effects from covariates to latent class indicators are present. This is joint work with Tiomara Sparhov. Direct effects represent measurement non-invariance, which is often present in studies with heterogeneous populations. Ignoring direct effects creates bias in the estimation of how the latent classes relate to covariates. Webtalk 9 presents new methods for detecting, accounting for, and evaluating direct effects for both single-step and multi-step latent class analysis. The talk is a companion piece to Webtalk 8, which describes multi-step latent class analysis. The central topic of Webtalk 9 is how to use penalized structural equation modeling, referred to as PSEM, to find the smallest set of important direct effects. This application of PSEM draws on techniques for regularized maximum likelihood estimation. PSEM extended to mixture modeling is discussed in a new 2025 article in the SEM journal by Tiomara Sparhov and me. And these techniques are included in Mplus version 9. Webtalk 9 is comparable to a research paper in that it proposes new methodology. The Webtalk format, however, provides more freedom to present ideas in more detail. Analysis illustrations use a real data set that is available for practice, and all Mplus runs are included on the website of the talk. Slide 2 shows the outline for the talk. First, I give a background for the situation that we're considering and discuss the problems of ignoring direct effects. Then I introduce the example that we're going to use throughout. And then I turn to discussing how to search for direct effects. And after discussing different approaches, I'm going to focus on penalized structural equation modeling applied to mixture modeling like LCA, latent class analysis, with direct effects. So we're going to refer to that as PSEM and apply that to the antisocial behavior example. And then we're going to discuss how one can evaluate these direct effects and understand if they're important or not. And we're going to introduce a new feature in version 9 of Mplus, a calculator feature. Then we're going to turn to the possibility of class-varying direct effects and extend the PSEM discussion to so-called PSEM diff priors and discuss the new output feature, the align option that goes with diff priors, where you can see the results of the class-varying direct effects very clearly. Finally, then we turn to multi-step analysis in line with Webtalk 8, where we then introduce direct effects and distal outcomes. And then I do a summary of this and points to needed further research in this area. Slide 3 shows an example of having direct effects from covariates to latent class indicators. In this case, we're taking a look at 6 binary indicators, U1 through U6, measuring a latent class variable C, where we have covariates x1 through x3 and distal outcomes y1 through y3. And we have 2 direct effects, one from x1 to u2 and one from x3 to u5. So there are direct effects. They do not go via C, but they go directly from x to u. So a direct effect implies that for a given class, conditional on C, the probability of u is not the same for different values of x. So different individuals having different x values will have different probability of u, even conditional on class. So that means that the measurement model parameters are not the same for different individuals, and that's referred to as measurement non-invariance or differential item functioning, diff, in the item response theory context. And it's also referred to as item bias. For example, with a binary X describing two groups, say males, females, the measurement instrument does not work the same for the two groups. Slide 4, then, I go through the analysis impact of ignoring direct effects. Consequences of ignoring direct effects. First one is the violation of conditional independence given C. So now, class enumeration, that is deciding on the number of classes, I'm claiming that the impact is likely small. And think about this example. Say that you have found 3 classes, or say that rather that there are 3 classes as the true state of affairs, but you have these direct effects, which means that U2 and U5 will correlate even given class because they're influenced by X1 and X3 that correlate. So you have this residual correlation between latent class indicators, which might lead you to choose 4 classes instead of the correct 3 classes. But the impact probably is typically not large. You may not often find more classes, a need for more classes. Now, you also have distorted model estimates in terms of class probabilities, typically small impact with or without using the X variables. So you have an analysis, say, with only the latent class indicators, no X's, but there are direct effects, and therefore correlation between U2 and U5 beyond that of C, that generated by C. So that I'm claiming is small, and even if you include the X's, it's also probably a fairly small distortion. However, C on X, the regression of C on the covariates, I claim has a large impact of ignoring direct effects, because the direct effects are forced to go through only C. So X1, which influences C and therefore indirectly U2, also has a direct effect, and when you don't allow that, X1's influence on C is likely to be increased to capture the correlation between X1 and U2. And we described that in a paper, 2014 paper in the SEM journal, which is largely the same as WebNote 15 on the Mplus website. Now, Y on X then, this part, the Y's regressed on X, I would claim that there is some impact, because when C on X changes, this C on X part here changes, the indirect effects of X on Y via C will change because of the change here. And therefore there will be a change in Y on X. So if the indirect effect via C changes, Y is influenced by C but also by the X's, then the influence of X onto Y directly, not via C, changes to some extent. And we'll see an example of that towards the end of this talk. I'm also going to cover multi-step analysis, where in this example it would be focusing on the distal outcomes Y here in the last step of the analysis. And the first step analysis then, which is usually the measurement model as we discussed in Webtalk 8. It's the measurement model, but in this case we're going to let the measurement model include the X part, include the covariates and its direct effects onto the latent class indicators. And then in the last step, add the distal outcomes. So turning to the outline on slide 5, we're now going to present an example that we're going to use throughout, antisocial behavior example that we also used in Webtalk 8. So here's the data set on slide 6. We have 17 antisocial behavior items, which constitute the binary latent class indicators, because we dichotomized the frequency of various behaviors during the past year. And we have a little over 7,000 respondents, and there's no missing data in this data set. I have analyzed these data before in structural equation modeling, mimic four-factor analysis. In this paper for the Cambridge University Handbook, you have the reference at the end of the talk. And also, when it comes to latent class analysis, in Mplus short course topic 5, where I look at both 4 and 5 class LCA for these 17 latent class indicators. And with 5 classes being high on all the indicators, property offense indicators endorsed only, drug, person offense, and a low normative class. In this talk, I'm going to work with 4 classes. Now, ASB, antisocial behavior data, that's a general population survey of young people, so that considerable heterogeneity among these individuals can be expected, which would mean that we should be able to see a lot of direct effects being significant. In this talk, I'm going to work with 2 versions of the data set. One version, the full version, I work with the 17 binary U indicators and 11 covariates. And I'm also going to work with the reduced set, where you only have 7 indicators and 7 covariates, and where you're going to work with 2 distal outcomes. On slide 7, we see the input for the analysis of the full set with 17 latent class indicators and 11 covariates. And in this case, we bring in the regression of the latent class variable C on the axis, but we have no direct effects yet. So we have the ASB data set here, and the use variables are the 17 indicators, property through gambling, and then we have the 11 covariates, sex through abuse. And we declare the indicators as categorical. They are binary in this case, dichotomized. And we ask for 4 classes. We have mixture modeling using ML and a good number of random starting values. And I use 12 processors to speed that up. And in the model then, in the overall part, we have C on all of these 11 covariates. And as usual, the latent class indicator thresholds or probabilities vary across the classes as the default, so we don't have to mention them. So with 17 U's and 11 X's, we have 17 times 11 equals 187 possible direct effects. So now we have to try to figure out which ones are important to include. On slide 8, we see the outline again. And now we're ready to talk about how to search for direct effects. And I'm going to talk through a set of different approaches with a special emphasis on penalized SEM, PSEM. So there are several different approaches for searching for direct effects in LCA. So let's consider an analysis with the latent class variable regressed on all covariates. So we have C on X. And in addition to that, we have several alternatives listed here. First of all, we can regress each latent class indicator on all covariates if we have an indicator that we worry about being non-invariant, or we can regress all latent class indicators on one covariate if we have a candidate covariate that we are worried about being a cause of a direct effect of non-invariance, like male-female. And the pro of that, the advantage is that each analysis easily converges, and the negative is that we have to do several analyses, one for each latent class indicator or covariate, depending on the alternative we choose. Another approach is to regress all latent class indicators on all covariates, and the advantage is then that we have a single analysis. And the disadvantage is that it may not converge, perhaps due to being empirically non-identified. It may not be empirically identified. We have to remember that in mixture modeling, it may be identified in principle, relying on higher order moments. If you compare with the non-identified case of mimic with continuous factor indicators, you cannot have all direct effects as well as the factor regressed on the covariates. So relying on higher order moments can be a little bit unstable, and it may not converge in all cases. Yet another alternative is the one we want to focus on here, namely, again, regressing all latent class indicators on all covariates using what we call PSEM regularization. And there are two papers related to that, the original 2024 paper and now a new follow-up paper which talks about extensions to the 2024 paper, and that includes PSEM for mixtures, that is, including then latent class analysis. And the advantage here is that it leads to parsimonious models, that is, with fewer significant direct effects, and it converges more easily for a small enough prior variance. So we can avoid the non-convergence problem that we may have up here. The disadvantage is that we have to choose prior variances, which calls for more than one analysis. So I'm going to illustrate that. So let's ask ourselves, what is PSEM then applied to finding direct effects in LCA? Again, PSEM stands for penalized structural equation modeling, and we're focusing on maximum likelihood estimation, which is what we use for mixtures, using priors. And PSEM in general uses priors for two quite different purposes. One is to estimate a model that is non-identified without the priors. So the priors add the extra information that is necessary to make the model identified. And that's very similar to what we call BSEM for Bayesian estimation, with small variance priors for parameters that would otherwise be non-identified. But it can also be used for the other purpose of simplifying models that are identified but can be fitted practically as well with fewer parameters. So that's a common situation in mainstream statistics. It's called a regularized analysis, where a common prior is the so-called lasso prior, which stands for least absolute shrinkage and selection operator. And lasso is used, for instance, in regression when you have many covariates and you want to pick out those that are important and setting the slopes for the others to 0. And in our case, the example is dealing with direct effects in LCA, latent class analysis. So what we're going to do is to include all direct effects and have PSEM use either lasso or another prior that we call ALF, an in-house prior, alignment loss function, with mean and variance priors for the direct effects. And what we're going to do is to maximize a fit function, which is the sum of the usual maximum likelihood log likelihood plus a penalty. And that penalty is larger for smaller variance. So for instance, we will specify an ALF prior with mean 0 and a small variance like 0.01. Now, the 0.01 mean and variance means that we have, since it's a small variance, the penalty is larger. We have a larger negative addition to the log likelihood, and we get a larger penalty for any direct effect that deviates from the mean of 0. Now, that means that the penalty penalizes model with many direct effects. It favors a parsimonious model. We don't want to have a large penalty, which we would get if we have many direct effects. Variance equals 0 exactly would be a very large penalty and hurt the maximization of the fit function. And that would then lead to a non-PSEM analysis, a regular analysis with no direct effects, because you don't dare to have any direct effects because they'll increase the penalty. Variance infinity, or very large, is the same as a non-PSM analysis with all direct effects. So you want to try to find something in between of the no and all. Use a variance that makes the log likelihood practically as good as with all direct effects included, but with fewer direct effects. Now here's the input. It's very simple. The theory is complex, and I'm trying to describe it in very short terms. But the Mplus run is very easy. The only thing we add are those bolded parts here in the model that we looked at before. In addition to C on X, we also have U on X. The latent class indicators regressed on all of the covariates, and there are then therefore 187 of those effects, 187 slopes in that regression, 17 times 11. And we give them labels, direct effect 1 through 187, and the model prior then is alpha for all of those parameters with mean of 0 and a relatively small variance of 0.5. And we're going to see how that works out. Here is the essence of the technique described in a picture. So on the y-axis we have the log likelihood, and it usually occupies the negative part, and the closer it is to 0, negative but close to 0, the higher the likelihood, the better the likelihood. On the x-axis we have the prior variance. So when the variance is 0 or almost 0, we have a very small variance, a very large penalty, and therefore a very parsimonious model. Here's a very parsimonious model. It's the model with no direct effects. So very small variance for PSM is the same as a non-PSM run with no direct effects. And on the other end of the spectrum, you have a very large variance, which is a small penalty, and a very non-parsimonious model. And here is one where you have all direct effects included in the model, of which 97 happen to be direct effects that are significant. Now you look at this likelihood that increases and then flattens out, and what you want to find is a smaller number of direct effects than 97. We started with 187 possible, 97 are significant. Now we want to reduce it down to a more manageable number, and we choose a number then somewhere on this curve where it is flattened out enough, where the likelihood value is close enough to the likelihood value here on the right. And that is obtained then with different choices of the PSM variance values that we're going to try. And here on slide 13, you have a very intensive description of what we do, the strategy that we take. So we have the models, number of parameters, log likelihood, BIC, number of significant direct effects, and something we call log likelihood drop. So first we start out with 3 non-PSM models. So PSM is not involved at all. The model with no direct effects, a lot of parameters, rather few parameters, and a very large negative log likelihood, so very low and bad log likelihood. And here you have the BIC, and there are no significant direct effects because there are no direct effects. And then you have the model with all direct effects. The number of parameters jumps, the log likelihood improves, gets closer to 0 from below than the one above. But it has more parameters, and BIC gets worse. The number of significant direct effects is 97. And then let's try to do an analysis with only those 97 significant direct effects. And the number of parameters then goes down, and you have this log likelihood, which is having the best BIC of the first three. So now we found a model that has a good BIC and 97 significant direct effects. And now we want to try to reduce the number of direct effects down without worsening this log likelihood value too much. So we have then a couple of PSEM runs for model 4, 5, 6, and 7, and 8. And we look at the log likelihood and see how much worse it is than this log likelihood. We start very low here, low negative, so bad log likelihood. And then we get up higher and higher in the log likelihood with increasing variance for the prior. And by the way, I should mention that the NA stands for not available, which means that for PSEM, as I will describe later on, the number of parameters is not a clear number. It's not clear what that number should be, and therefore we also lose BIC here when we use PSEM. So with the lowest variance here, 0.05, we get 10 significant direct effects, but the log likelihood is pretty far from the one with 97 direct effects. Increasing the variance a little bit, get more direct effects, improving the log likelihood. And then here for 0.5, we get 42, 42 again, and then 53. So we are then moving up on this curve here by increasing the variance for PSEM, moving up and improving the log likelihood. And after we've done that, then we can get back to non-PSEM runs for the last couple of models from 9 to 13. So for instance, building on model 4 with PSEM 0.05, we had 10 significant direct effects. So we have then a non-PSEM run where we allow 10 direct effects and look at the log likelihood and BIC for that. And then we have, let's go down to model 11, which builds on model 6. So that 6 here refers to the model up here, so 0.05. For model 6, we had 42 significant direct effects. So we have 42 direct effects here. And here's the log likelihood and the BIC. And it turns out that only 41 of those were significant in the non-PSEM run. We also have the model building on the non-PSEM model 12, building on the PSEM model 7, where we also had 42, but it's not the same 42 direct effects in models 11 and 12. Both models 11 and 12 have 41 significant direct effects. Compare that to model 3, where you have 97 direct effects. So we got a big simplification here. And the worsening of the log likelihood is relatively small. If you look at this log likelihood compared to these, they correspond to only a 0.2% drop. That is worsening of the log likelihood, computed as this percentage here at the bottom. So let's take a closer look at choosing between models 11 and 12. On slide 14, why is 42 for PSEM 0.5 bolded in the graph on slide 12? Let me go back to slide 12 here. Why is this 42 bolded here? Why do I choose that over that, for instance? Well, PSEM 0.5 model 6 has a lower, that is worse log likelihood than PSEM 1.0 model 7. And both models show 42 significant direct effects, but not the same ones. Now the non-PSEM models 11 and 12, which are based on the PSEM models 6 and 7, for them, freeing the 42 direct effects results in a higher log likelihood for model 11 than for model 12, despite model 6 having a lower log likelihood than model 7. So this is why we lean towards model 11 rather than 12. We have a better log likelihood for model 11 and for model 12. Model 11 and 12 have the same number of parameters, same number of significant direct effects, and the same log likelihood 0.2% drop. Model 11, however, is chosen because it has the better log likelihood and better BIC than model 12, and it actually has the best BIC of all the models. So in the outline on slide 15, we now turn to the antisocial behavior example in the reduced version, the smaller sized version. And we're going to focus on latent class probabilities and particularly on C on X results, regressing the latent classes on the covariates. On slide 16, you have the data set, ASB3, and the use variables that we're going to work with are these 7 latent class indicators and these 7 covariates. So this reduced set of 7 U's and 7 X's is perhaps more typical numbers of indicators and covariates that you will have in your data. It's not often maybe that you have 17 U's and 11 X's. So maybe this is a more typical example. The categorical variables are still the latent class indicators, and here are 2 setups on slide 17 where we regress all latent class indicators on all covariates. First, in a regular run, all U's and all X's, where we have a mixture and a good number of starts, and we have C on X and then also U on X. Now the PSEM run corresponding to that same model is adding to the direct effects regressions here labels and model priors. So this is all you have to do here. D1, direct effect 1 to 49, there are 7 U's, 7 X's, 7 times 7, 49, and we choose a prior of 1.0 in this case. And that's all you have to do to turn the non-PSEM run on the left into a PSEM run on the right. The computing time here is 1 minute, and you can note then that the larger set, 17U, 11X's, took 11 minutes. So the number of variables makes a difference, and I would say these runs are a little bit slower than what typically would be expected because the sample size is large, over 7,000 people. So slide 18 then, we have this log likelihood graph again, the log likelihood on the y-axis and the prior variance on the x-axis. And then we have a log likelihood curve here, which we draw approximately from our results. It's not generated by Mplus. And we see that when we have an all direct effects run, the non-PSEM run with all direct effects, we get 22 significant direct effects of the possible 49. And down here we of course have no direct effects, which is a non-PSEM run, but it's the same that you would get in a PSEM run if you had a very small variance. Now this number 19 here in the middle, the fact that the number of significant direct effects does not increase monotonically here is not what we would generally expect, but it can happen. So slide 19 then gives this log likelihood table again that we saw for the full set. We have the no direct effect model with the lowest log likelihood and no significant direct effects because there are no direct effects. And then the all direct effects run with 22 significant ones. And then we do a run with only those 22 significant direct effects. And that then is the beginning of our analysis before we turn to the PSEM runs here with different variances for the priors. Here we go from 0.1 to 1.5. And we see then that the PSEM 1.0 run has 15 significant direct effects, and we get the same 15 direct effects in the PSEM 1.5 run, and here actually the 15 direct effects are the same in models 6 and 7. Turning to the non-PSEM runs down here, building on model 4 with 10 direct effects, or model 5 with 19, and model 6 with 15. We see the log likelihood, and we see the BIC values here, where the BIC seems to be the lowest for of them all for the 19 direct effects, but the 15 direct effects model comes very close. And in both cases, 19 and 15 direct effects, actually 14 of them only are significant here, you have a very small log likelihood drop as defined by this percentage here. Now let's take a closer look at these models. Why did I bold 15 for PSEM 1.0 in the graph on slide 18? So let me just go back to slide 18 for a second. Why did I bold this one and not 19 or that 15? Well, model 6 and model 7 have the same number of significant direct effects, so it doesn't matter that model 7 has a higher log likelihood, because both models lead to the same non-PSEM model 10. Same direct effects. I chose model 10 because it has a small 0.2% drop in the log likelihood. It's relatively parsimonious and is close to the best BIC. But model 9 is a strong contender. So that's the model 9 here with 19 direct effects and a 0.1% drop. Strong contender with a smaller drop in log likelihood, the best BIC, but 19 instead of 15 direct effects to consider. So not as parsimonious. Model 3 is also contender. Let's see, model 3 with 22 significant direct effects. That has a BIC which is very close to the one with 19 direct effects. So almost the same BIC as model 9, but 22 instead of the 15 direct effects. So you ask yourself, how parsimonious can you go here? How few direct effects can you get away with? And the question then is, are the extra direct effects of model 3 and model 9 relative to model 10, are they important? So I took a look at that for model 9. The fight indicator on the dropout covariate is the only noteworthy direct effect beyond those of model 10, with a fairly small probability difference for non-Hispanic males at average age 94, varying the dropout from 0 to 1. Now slide 21 gives some technical notes here. First, we talked about a number of parameters for PSEM earlier, and I wrote not available, which means that you don't get BIC either, because that is based on the number of parameters. And that's because when you do a regsem, that is PSEM applied to models that are identified, but that you want to simplify, that doesn't have a good way of counting the parameters. Parameters, like it says here, can have tiny prior variances with parameters estimated close to 0 and contributing nothing to fit. And we argue that these are not real parameters that should be counted, but the precise removal of these parameters is subjective, etc. You need the definition how close to 0 we really are. So it's not clear what the number of parameters is in this regsem version of PSEM. That's one point. Another technical point is that you can come up with alternative log likelihood drop definitions And here's one that is favored by Tiermer, where the denominator here is the difference between the model LM1, which has no direct effects, compared to the model with all direct effects. So if we go back to the slide on 18 here, we're talking about the model with no direct effects and the model with all direct effects. So as a denominator, you look at the difference between the lowest and the highest point of the log likelihood, and then you talk about how much changes within that range for different model choices. So back to slide 21, you take your model, particular model that you're interested in, subtract it from the M2 model. Again, the M2 model is all direct effects, and then compare it to that full range of likelihood difference. That's for PSEM models, and he suggests for models, for non-PSEM models, that is models based on PSEM but not using PSEM, you have a different denominator here, where you compare model 1 and model 3. So model 1 and model 3, no directs versus 22 significant directs. So that's the non-PSEM denominator. Now, in this case then, the percent drop relative to the total possible drop should be a small value, like you can have a cutoff where you would want it to be at least no higher than 5%. So if you go back and use that new idea for the full set of variable run that we did earlier, model 11 does best, which is the same model that we chose before. So that doesn't change the choice. But here now, for the reduced set of variables, model 9 does best, the one with 19 direct effects, which has a 5% drop, whereas we chose model 10 with 15 direct effects, which has a 17% drop. So not as satisfactory in terms of a drop as model 9 with 19. But again, are the extra direct effects important? All right, now let's turn to the latent class results and the C on X results for the model I chose. So let's interpret first of all the 4 latent classes for this model 10 with 15 direct effects. So the classes are fighting, threatening, high on all the indicators, high on drug indicators, and low on all the indicators. So I use the output section results in probability scale, which is useful especially for binary latent class indicators. It's probability of being in the high category of the indicator, that is, you have experienced this. So class 1, the fight threat class of 0.32, 321 people. Fight and threat are high. Class 2, high on all of them. Class 3, high on pot and drug. And class 4, low on all of the indicators. So slide 24 then gives the class probabilities for this reduced model. We get the same interpretation for the different approaches here that I list. And the first approach is model 10, class probabilities with 15 direct effects, 0.321, etc. Now, if you don't include the direct effects, you get slightly different probabilities, but not a huge difference. But if you do what's often done, compute the class probabilities based on the latent class indicators only, that's certainly what we do in multi-step analysis, where the latent class indicators constitute the measurement model, which we use in the first step. Then you have a bit lower class probability for the first class, and a little bit higher class probability for the last class. So there you have more of a difference in the class probabilities. Then you may want to ignore. So again, this is the model we choose. Here's the model we may pick incorrectly. Slide 25 then. The central result is the C on X, the regression of the latent classes on the covariates for this model. On the left and on the right we have the no direct effect model. And we look at class number 1, which is the fight threat class. And you see then for model 10, Hispanic has a significantly lower effect on fight threat, significant and negative. Divorce has a significant increasing effect on fight threat. But if you ignore the direct effects, you see the Hispanics have a positive effect instead of a negative, and it's insignificant. And for divorce, it's also insignificant. It has a smaller estimate and a slightly larger standard error, becomes insignificant. So this is a difference that may be important in your analysis, and this is just showing it for one class. Now, number of significant effects of covariates on all the latent classes. In the 15 direct effects model, model 10, we have 17 of them. In the no direct effect model, that is the one on the right, the total number is 13. So one can ask, why do we have fewer significant direct effects in the, fewer C on X effect, significant C on X effect for the model with no direct effects than the one with 15 direct effects? It could be that when direct effects in the no direct effects model are forced through C only, the effect of the covariate on the latent class indicators are forced to go through C only, some significance is lost. Maybe direct effects with opposite signs are present. These kinds of discrepancies up in this table at the top here were found in simulations in the 2014 paper by Tiemer and me, which is pretty much the same as WebNote 15. We're now ready to take a look at how to evaluate direct effects. So we're going to look at the results from the analysis of the reduced version of the antisocial behavior example and introduce a calculator that will be useful. So slide 27 then, here are the 15 direct effects for the reduced model using the model 10 version that we have settled on. So we have for the property item, we have direct effects that are significant from sex, black, divorce, age 94, for fight, sex, Hispanic, age 94, etc. down for the 7 items. So all of them have direct effects of some kind or another. On slide 28 then I showed the direct effects for the property and fight indicators, the first 2 indicators. So property on sex, black, divorce, if you go back one slide, sex, black, divorce, and age 94, and for fight for those 3 direct effects. So we see that property on sex, so that's a dummy variable for male versus female, is a significant positive effect. And for fight, we're going to focus on the same covariate, and notice that that has a slightly smaller direct effect for the fight indicator than for the property indicator. Still significant, however. Now, the effect on the probabilities, however, depend not only on these slopes in the U on X regression, so to speak, the latent class indicators regressed on the covariates, but also depends on the indicator's thresholds. So we're going to take a closer look at how that works. So slide 29 lays that out in terms of a probability curve. So we have a probability on the y-axis here, and that curve, the probability increases as a function of a logit. So we're working with logistic regression here for the indicators. So probability is equal to 1 over 1 plus e to the power of minus logit. So this familiar logit probability relationship, that formula is what's used to describe this curve here. And we're going to say that in this curve, it is much steeper at this point of the logit values. That is, a certain distance here between logits makes for a large difference in probabilities as compared to the same logit difference down here, lower on the curve with a lesser slope, making for a smaller difference in the probability. So I'm trying to say that the probability differences, for instance, between males and females, depend on where you are on the x-axis here. So let's take a look at that in some detail for a minute. So the logit here in this case is equal to minus tau subscript c, where tau sub c is a threshold for class C, and then you have beta times x. Beta is the direct effect of, say, males versus females. So that's the equation. And we're saying then that the small probability is obtained with a large threshold. And the probability up here is the probability of the indicator u being 1 as opposed to 0. And a small probability is obtained with the large thresholds. I mean, it's hard to exceed the threshold. They have a small probability of it exceeding the threshold. And a small probability, large threshold, small logits. So thresholds and logits are in opposite directions. That's why we have minus threshold here for the logit. Now the largest probability change from x equal to 0 to x equals 1 in this equation for the logit occurs at the steepest part of the curve with threshold close to 0, that is probability close to 0.5. Probability 0.5 is where you have the steepest part of the curve. And note that logit equals 0 gives probability 0.5 by this formula here. E to the power of minus 0 is e to the power of 0, which is 1. So in the denominator we have 1 plus 1. So the probability is 1 divided by 2, 0.5. Okay, so those are the basics here. Now let's take a look at the example where we do direct effect probability calculations for the property and fight indicators. We're going to compare males and females for the fight and threat class, which is the first class. And the Model 10 estimates are as follows. For the property indicator, we have a threshold of 1.352, a high threshold, meaning that it's less likely for people to admit to that indicator or that activity. And the direct effect is 0.676, which gives you a logit of minus 0.68 when all the other x's are 0. And the x's are largely binary x's, so setting them at 0 is a reasonable value. Now for the fight indicator, the threshold is smaller, and we have a higher likelihood in general to have people admit to that. And the direct effect, however, is smaller. So that gives you a logit of 0.37 when other x's are 0. So this logit is smaller, or closer to 0 rather, than that, which means that the curve is closer to 0.5, where you have the steepest part. Now, probabilities for females versus males at 0 values for all other covariates except H94. Let's consider that. H94 is the only continuous variable, so setting it at 0 is not necessarily relevant, although it is in the range of H94. But setting it at its sample mean instead, you get these values for females. Property 0.161 versus male 0.274. So males are more likely to engage in that, whatever that indicator measures. And the difference is 0.113 between those two values. For the fight indicator, females have the probability 368 and males have a probability of 0.511, and the difference is a little bit bigger. So even though the slope is larger for property than for fight, the difference in probabilities is larger for fight than property. That's the point I wanted to make. So that's what I spell out in the last bullet here. Which you have now read, I hope, and it concludes with the direct effect slope size alone does not tell the whole story about how important the direct effect is in terms of the probabilities. So now let's focus on this calculator that I mentioned, and that is a new feature in Mplus version 9. The Mplus calculator existed for latent transition analysis, and here we expanded it to calculating direct effects and also actually direct effect probabilities, and also actually with class varying effects we also compute odds ratios. So anyway, computing direct effect probabilities conveniently can be done by pulling down the Mplus menu here in the output and clicking on calculator, and then you get this window, conditional probabilities for latent class indicators or conditional probabilities for latent class variable as a function of covariates. So we click OK for the conditional probabilities for the indicators, and here's what we get when we set it for male equal 1. So I go back and forth here between sex equal 1 or male equals 1, but same thing. So what you do here then is you click on the covariate, and then you click on assign value, and then you put in the value, 1 in this case, and then click apply, and then you click on OK. And out comes this result. Male 1, black, Hispanic, single, divorced, dropout, all 0, but the remaining covariate age 94 is set at its sample mean. So the conditional probabilities then are given for the different indicators. We're focusing on the first two here, and the columns then are the latent classes, and we're focusing on class 1, the fight threat class. And we're interested in the highest probability, no, sorry, the highest category of property, which would be corresponding to u equals 1 versus, as opposed to u equals 0. So we're looking at 0.274, and for fight we're looking at 0.511, which is what we saw on slide 30, if we go back to that. 274 and 511 is what we calculated at the sample mean of age 94. Going back to slide 34 then, we can go on to slide 35, where we do the same thing for male equals 0. So you have male equals 0 here, and then you get the value 0.161 and 0.368, which is also the same as what we have on slide 30 in the middle for females. Now we have a convenience feature in the calculator shown here on slide 36, where you can copy sets of values for covariates. So this is convenient when you compare, for instance, sex equals 0 to sex equal 1. You don't have to type in the other covariate values again, but you can save them. And it's also convenient if you change only a few covariate values. So you enter your values for the first set, click on the button above the OK, cancel, apply, copy values to new set. That will copy all the values you just entered to a new set. And then if you look at the top of the display, you see a second default tab will open to the right of the original default tab with the copied values that you can then edit. changing, for instance, the sex from 1 to 0. And you can even change the label of that tab. And then you click OK, and probabilities for both sets will be shown, one below the other. Now, the calculations that are done behind the scenes in the calculator can be done also using model constraints. So if you do direct effect probability calculations for the property indicator, for instance, comparing male equals 0 versus 1 and all other x's equals 0 except H94 sample mean, then you do it this way. So you have the model here, C on the axis and the indicators on the covariates, so U on the axis here. And what you do is you label what you're interested in. You're interested in the property on male, you're interested in H94's influence as well, and since you're dealing with a property indicator, you want to also have its threshold in the first class here, which we're interested in. So we label that by T1. So these B's are the betas in that equation that I talked about earlier, and this T is the threshold. And then in model constraint, you compute logits and probabilities with the suffix 01 corresponding to male 01. Sample mean of H94 turns out to be 2.957. So you have then, let's take a look at a logit for male equal 1. That's equal to minus the threshold, as we shown in the formula earlier, plus the coefficient B1 for male, times 1, which is the male dummy variable value, plus B2, the coefficient for H94, times its mean value. So for sex equals, or male equals 0, we don't have B1 because B1 times 0 is 0. So then we have those logits, and the corresponding probabilities are then the ones plugging the logits into the exponential function here with a negative sign. And out come the values that we saw earlier on slide 30. Now we turn to class varying direct effects, where we can also use PSEM, introducing the topic of diff priors that concern comparisons across classes. And we're also going to introduce the align option. And all of this is new for Mplus version 9. So on slide 39 you have the input, and again we're working with the model 10 setup with 15 direct effects. But now we're going to allow those direct effects to be class varying. So we have the use variables, the 7 indicators, and the 7 covariates. Mixture modeling estimator should be equal ML here, and with a good number of starts. And we have C regressed on the covariates. And then in the overall model, we also have to mention the direct effects. But we're going to focus on the class-specific mentioning of the direct effects, so making them class varying. So for instance, for property on sex, black, divorce, H94, we're going to label them A1 through A4 for those 4 direct effects. And then we continue on adding the numbers for the other direct effects, coming up to 15 direct effects. And for class 2, we then go to label them as B instead of A, going from 1 down to 15. For class 3, we use the letter C, and for class 4, the letter D. So what we have here then is the new setup of do-diff priors. And the do-diff works as follows. We're allowing for class differences for each direct effect, and we're studying those class differences here we're letting the difference between these classes for these direct effects to have an alpha prior with prior variance 1.0 in this case. So the way you read this, instead of this hashtag here, you put in the number 1 through 15. So first we take a difference prior for A1, B1, C1, D1. So that is comparing the 4 classes. A, B, C are the 4 classes, and the numbers 1 through 15 are the 15 direct effects. So we go first looking at A1, B1, D1, C1. So that is, if you go back one slide, A1 is property on sex in the first class, B1 is property on sex in the second, etc. Property on sex for the 4th class, namely D. Okay, so that's a very convenient way of writing it, and it's not too complicated once you have explained it. Then we have the align output statement here, which is going to compare results across classes for each of these direct effects in a very informative way and concise way. So on slide 41, I take a look at the results for applying class varying direct effects. Again, model 10 with 15 direct effects now allowed to be varying across classes. So here is the result for the PSEM run with the 1.0 variance for the diff priors. So the diff priors have mean 0 and a variance of 1.0. So we're trying to keep these differences close to the mean of 0 for the prior and rein them in that sense, keeping them to a minimum. And that gives this log likelihood value. BIC is not available because we don't know quite how to compute the number of parameters, as we said before. Now, if you do a non-PSEM run with class varying direct effects, you get a likelihood that is better, it's higher, but you get 2 fixed direct effects that could not be estimated. So here we run into the problem of empirical non-identification, which can happen when you do regression of all the indicators on all the covariates, especially when you allow them to be class varying. So in this case, you would prefer the PSEM run, also because the difference in the log likelihoods is not that large. You can do that percent drop in log likelihood calculations that we did before. Now, if you look at the third bullet here then, what about the class invariant case of direct effects using non-PSEM? Well, that one has no problems of fixed effects, and you get a BIC value of over here, which you can compare to the non-PSEM run up here, and you see then that class invariance gets a lower BIC. So the class invariant direct effects is a better model than the class varying direct effects. So better BIC than for class varying direct effects, and no need for class varying direct effects in this example. However, we use this example to illustrate PSEM with diff priors because that is useful with situations where we do have class varying direct effects. And we're going to take a look at the align option in the output, which shows which effects have significant differences across classes. And that's in line with, that's drawing on the ideas of factor analysis alignment across groups in this 2014 paper and other papers listed at the measurement invariance section of the Mplus website. So on slide 42, you see the alignment option with PSEM diff priors. And again, let's remind ourselves about what we have here. The letters refer to the 4 classes, A, B, C, D. And the numbers refer to the direct effects. So if you go back to slide 39 here, you see then that you have A for class 1, B for class 2, etc. And if you look at A1, it's property on sex, the first one of the direct effects for the property item. Going back to 42 again. So we're looking at property on sex, comparing the 4 classes here. Now, first we didn't get a chi-square output here, which is small relative to the degrees of freedom. That is very small class difference in that particular direct effect. So probability is very high that there is no difference. So no significant class differences. So that points towards class invariant direct effects, which the non-PSEM run for with BIC, comparing BICs, also indicated. And we see then out here that we have no significant, no low p-values for any of the comparison, B versus A, C versus A, C versus B, etc. So we're saying then that we're concluding that approximate invariance holds for this direct effect across the classes, and the average value is 0.683. So average of all of these values listed up here. And you have the difference between each here, and you see then that you don't have any significant p-values here. Slide 43 then. Again, letters are classes. We're comparing the 4 classes. And the number 11, let's go back to slide 40 here. Number 11, that's pot on H94. And we're going to compare that across all of the classes. Back to slide 43 rather. So we're talking about pot on H94, comparing the 4 classes. And in this case then we have a borderline significance for testing the class differences. And we can then look at where that borderline significance comes from and look at small p-values here. And we see that the smallest one is for comparing C11 and B11. So that's pot on H94 comparing the 3rd and the 2nd classes. And those are the pot and the high classes. So those who are substantive experts here can try to figure out what that means. So that shows you the usefulness of the alignment output in conjunction with the do-diff prior approach. So now we're turning to multi-step analysis with direct effects and distal outcomes. So now, adding distal outcomes to the analysis of direct effects. What are the steps? Well, the first step is the measurement model, but in this case, the measurement model will include the covariates and the direct effects. And what should the last step look like? Well, we're going to take a look at that for 3-step BCH and 2-step. These multi-step analyses that were introduced in Webtalk 8. So we're going to work with the reduced ASB data, with the 15 direct effects of Model 10, adding alcohol dependence and abuse as distal outcomes. And we remember that these are strongly skewed variables with large floor effects, treated as continuous in these analyses for simplicity. And it turns out that they're likely to be correlated even when conditioned on latent class. Slide 46 then. What does this input look like for the first step? Well, we have the use variables of the latent class indicators, those 7, and the 7 covariates. And we're going to save the distal outcomes, dependence and abuse, using the auxiliary option for the last step analysis. And here we have an up seed instead of a start setting, and that's because we have done a previous run where we want to do a reordering of the classes using the S values option. So we want the classes in a different order, and this is the follow-up run to that. So what we have here in the model is C on the covariates as before, but now we add the direct effects for property, fight, etc. down. And we're going to save C probabilities and BCH weights into a final data set, and we also ask for S values here, so we're going to get the S values saved as well. So this is what I call the combined approach, where we in the first step we prepare for all three multi-step methods: 3-step, BCH, and 2-step. C probs are used for 3-step, BCH weights are used for BCH, and S values are used for 2-step. So now let's turn to the last step, and in this case for the 3-step approach. And the use variable list is then the covariates and the distal outcomes and the nominal most likely class indicator N, which is a hallmark of 3-step analysis. And we give starts equals 0 that we usually do as a standard for the last step. I'm going to discuss the alternative starts later on. So the model then has dependence and abuse regressed on the covariates, and we also allow for within-class covariation between dependence and abuse, since these are strongly correlated variables. We don't include any direct effects here, since the indicators are not in the model. You know, direct effects involve indicators, but that they are not on the use variable list in 3-step. They're sort of condensed into the nominal N most likely class information, which we fix down here in the logits for 3-step. So the direct effects play a role only in the first step. Let's go to BCH and its last step. Use variables are like before, except we also have the BCH weights, and using the training option we get the weights for BCH that it needs. The model is the distal outcomes on the covariates and the within-class covariance between the two distal outcomes, and no direct effects since indicators are not in the model. They're not on the use variable list. All the information from those indicators are condensed into the BCH weights. Slide 49, then we have the third method, 2-step analysis, last step. And then the use variable list changes. So it's a 2-step method where we fix the measurement model, parameters of the measurement model from the first step analysis. So you have them, the indicators here, property through through goods rather, and then the covariates. And again, this is a starts equals 0 situation because it's the last step. And we do dependence abuse, the distal outcomes on the covariates, and within-class correlation, and input continues on the next slide, where we have the direct effects needing to be included here in the last step because the indicators are in the model. So we list them all here in the overall part of the model, and we have the C on X part fixed. And then for class 1 we give the labels for the different direct effects. We give the label for property on sex, for instance, here fixed at the first step analysis. Give the label 29 here just to remind ourselves that it's going to be the same as for class 2 and 3 and 4. Now it's fixed, so the labeling doesn't even matter here, but it's just for pedagogical reasons I kept them. All right, so that's 2-step. Now let's take a look at slide 53 and what the results are. So the class probabilities from the first step, Model 10, 15 direct effects that we looked at earlier in this talk, where we did not involve the distal outcomes. We have them here for the 4 different classes. Now, class probabilities in the last step then, using starts equals 0, what we typically use, what we should use. 3-step, 4, 6, 1, 19, 1, 6, 4, 3, 5, 6. So you see the failure here. These values are quite different from those of the first step. So that's a failure, which is also seen in simulations in our 2014 paper. We have an undesirable influence of continuous distal outcomes. BCH, however, gives very much the same probabilities for the 4 classes. So the first and last step agree very nicely. And that's the case also for 2-step. But we're going to make a comment on 2-step a little bit later here. Now, you can explore, if you want to, but shouldn't be a standard procedure, starts greater than 0. And for 3-step, you get a better log likelihood, but it's not replicated. That's bad. The class probability is still different from the first step, and you get different estimates for the distal outcomes rest on covariates. So the solution, again, is influenced by the distal outcomes, which is not what we want. So that really knocks down 3-step in this case. BCH, same solution as for starts equals 0. That's what we want to see. So BCH is trustworthy. 2-step, you get a better log likelihood. You get the same class probabilities again, like we did there. But you get different estimates for distal outcomes rest on covariates. So that's not what you want. Solution influenced by distal outcomes. So the distal outcomes don't follow the assumptions of the model. And we conclude that BCH is preferable, and exactly what we found in our WebNote 21 and in Webtalk 8, and it's due to within-class non-normality of the distal outcomes. They're very non-normal in their distribution, and they're non-normal within class as well, violating the assumption of the model. So BCH is the way to go here in this example. All right, so on slide 54, we look at the results for the distal outcome regression in BCH, the last step. So we have the solution here, and it concerns y on x, and it is the case where we have covariates and 15 direct effects applied in the first step, but the results here are from the last step analysis, where we have dependence on abuse as dependent variables regressed on the covariates. We find significance for several effects, y on x, and now we're going to compare this solution from last step of BCH with the solution that we get if we only use the latent class indicators in the first step. That is, we do not use direct effects at all in the first step. So you have then for dependence, you have the same pattern of significant and non-significant effects. So for dependence, there's no difference really in ignoring the direct effects in the first step. For abuse, however, we look at the Hispanic covariate here. It is suddenly significant when we ignore the direct effects in the first step. It's a larger negative effect, about the same standard error, and it becomes significant, whereas it was not significant in the model that included the direct effects in the first step. And for H94, an insignificant effect becomes significant when we ignore direct effects in the first step. So we see that, as we mentioned early on in the talk, ignoring direct effects has some impact in the y on x regression. In this case, it happens for one of the two distal outcomes. All right, we're now ready to do a recap of what we've done and point to some further research in this area. So on slide 56, we take a look once again at the picture that we started off with the 6 indicators of a latent class variable and 3 covariates, some of which have direct effects on the indicators. And towards the end of the talk, we added distal outcomes and looked at their regression on the covariates. So without the distal outcomes, we took a look at models that included the direct effects and models that ignored them, including the axis, but ignoring the direct effects. You could also look at models that don't include the axis, as we have done later on. We compared approaches 1 and 2 with respect to C on X, this part of the model, and found that there were some important differences in this example, as it typically would be when ignoring direct effects. And then we turn to analysis with the distal outcomes, multi-step approaches like 3-step, BCH, and 2-step, where we found that BCH worked the best. And there we looked at the alternatives like including direct effects in the first step, which is what we advocate here, versus ignoring direct effects in the first step. And here's another alternative, including direct effects only in the last step, which would be relevant for 2-step, where you have that opportunity because you have the indicators in the last step analysis. I don't know why one would want to do that particular analysis. However, I don't think it has any advantage. And we took a look at excluding covariates in the first step using a measurement model that included only the indicators, which is the standard in multi-step analysis, but adding covariates in the last step, ignoring the direct effects. And we compared approaches 3 and 6 with respect to y on x and found that there were some distortions of the results when ignoring the direct effects. Now, further research then, well, there's a lot more that needs to be known about direct effect analysis, particularly with respect to the PSEM approach. And one can imagine then doing Monte Carlo simulation studies of the PSEM approach, as has been done to some extent in Asparov and Mutean, the 2025 PSEM paper, extending the original 2024 paper to other situations, more general situations, including mixtures. And figure 12 shows how to do Monte Carlo simulation studies using PSEM. But ultimately, you may also need the Mplus automation approach, which is described on the stat model Mplus webpage. And here's a caveat right now. PSEM needs to be further developed for the ordinal case, because you get into so-called threshold collapse when you include direct effects. Thresholds for adjacent categories of the indicator fall into each other and causes problems, convergence problems. But PSEM seems to right now work well for dichotomous and continuous outcomes, probably works well for count outcomes as well, although I haven't tried that yet. Now, this approach that we talked about, which is LCA with direct effects, so single latent class variable, is relevant for other settings as well, including growth mixture modeling. If you take a look at the model at the bottom here, you have 4 time points, and you have a covariate x here, and you have growth factors, which are influenced by C, that is changing the means of these growth factors for the different classes, the trajectory classes. And x's influence the growth factors even within class, even conditional on class, as shown in the picture here. And you have a distal outcome here, it's a U. That would be relevant as well. This is a model that was described in our 1999 biometrics paper, and further on in other papers. This book chapter has an interesting discussion of it, of different ways of misspecifying the model. And we talk about it to some extent in Web Note 15 as well. So here you have the possibility, you have the effects of X on Y, but indirectly through the growth factors. So imagine that you have 10 X's here, and you have 4 Y's, then you have 40 potential effects of X on Y via S, but beyond C, so it's a indirect direct effect, so to speak. And PSEM could help you study how many of these extra effects within class effects are needed for the model and simplify the model. And that can also be done then with respect to a distal outcome in a multi-step PSEM analysis. So that's the end of Webtalk 9. Here you have the list of references. Thanks for listening.